we've talked about titrations, and we talked about how they are a neutralization reaction, how we are reacting acid with base. So now let's actually do some calculations involving titrations, involving those experiments, so you know how to identify where the equivalence point should be and how to find information at different points along the curve. So here is a very simple problem that is faced all the time as you're doing titrations. It says, how many milliliters of 0.085 molar NaOH are required to titrate 40 milliliters of 0.0900 molar nitric acid to the equivalence point? So I have, if you think about your lab setup, my sodium hydroxide is in my burette, my nitric acid is in my beaker. So I have 40 milliliters of acid in a beaker, and I'm going to add sodium hydroxide to it. And they want to know how much sodium hydroxide do I need to add in order to get to the point where I've neutralized my nitric acid. Now, the thing that you have to remember about all acid-base titration calculations is this fact. At the equivalence point, the moles of acid equal the moles of base. Okay? So they want to know how much base do I need to add. So since I'm looking for information about the base, I'm going to find how many moles of acid I have. So what I'm going to do is I'm going to take the molarity of my acid times the volume in liters. And this is going to give me the moles of acid. And the reason I take the molarity times the volume is you have to remember that molarity is equal to moles over liters of solution. So since I have the molarity and I have the volume, I multiply the two together to give me the moles of my substance. So I whip out my handy dandy calculator and I say, okay, 0.09 times 0.04 is equal to 0.0036. So that's how many moles of acid I had in my beaker to start. Now I have to remember, at the equivalence point, the moles of acid equal the moles of base. So this 0.0036 moles of acid is also equal to the moles of base. So I know I have 0.0036 moles of base needed to get to the equivalence point. Well, the question says how many milliliters of 0.085 molar NaOH are required. So I go back to my molarity formula and I say, okay, 0.0850 is equal to 0.0036 moles at the equivalence point divided by X liters. Cross multiply, solve for X, go back to my calculator, and I take my 0.0036 and I divide by 0.85, I divide by 0.085, big difference between those two numbers, and I get an answer of 0.0424. 424 liters. But the question says how many milliliters. So I multiply by 1,000 and I get 42.4 milliliters of base are required. Now I look at this and I go, wait, that's fairly close to the number of milliliters of acid that I started with. Well, look at the problem. Notice my molarities are very similar. All acid-base titrations are, I'm sorry, not all. All the acid-base titrations will always be 1-to-1 ratios. So if your molarities are the same, that means the volume of each will be the same as well, okay? Because the moles will be the same. So I'll say that again. If your ratio of acid to base is 1-to-1, so in other words, I take one H plus and transfer it to the hydroxide, and that one hydroxide reacts, as will happen in almost all strong acid, strong base titrations. They will be 1-to-1 ratios. So if it's a 1-to-1 ratio, then if your molarities are the same, the volumes will be the same as well. Hint, hint, that's important for your labs. Okay, so in this case, notice my molarities are very similar, but they're not the same. It's still a 1-to-1 ratio, so since the molarities are similar, I would expect the volumes to be similar. I had 40 milliliters of the more concentrated acid, therefore I'm going to need more milliliters of the weaker substance, which happens to be the sodium hydroxide, and that's what I got, 42.4. Now let's do some more calculations involving situations along a titration curve. So the question here is, what is the pH of the previous solution? So the solution I just had on the page, had on the screen, which was a 0.0850 molar NaOH combining with 40 milliliters of 0.0900 molar nitric acid. Okay. Oops. Kind of wrote over my words. So it says 20 milliliters of sodium hydroxide have been added. Okay, so they want to know what is the pH after I've added 20 milliliters of base. Well, I know that my equivalence point is 42. It will occur after 42 milliliters have been added. So this is well before my equivalence point. And again, I know that because of my previous slide where I calculated the volume at the equivalence point. So it says, what is the pH of the previous solution after 20 milliliters of sodium hydroxide have been added? Well, what you have to remember about these situations are, these are neutralization reactions, which means the acid is canceling base. Okay, or base is canceling acid, depending on how you want to view this. So they want to know, what's the pH? Well, in order to find pH, I always write down my formula first. I know that I need to find my H plus concentration. And I know since I'm dealing with a strong acid, the concentration of the strong acid is equal to the concentration of the H plus ions. So I need to find the concentration of my acid after I have neutralized some of it with base. So what I'm going to do is I'm going to find the moles. Step one is to find the moles of each substance. So I have 0.04 times 0.09, which I know from my previous slide is 0.0036 moles of my acid. Okay. Now I'm going to find the moles of my base. Well, I have 20 milliliters of a 0.085 molar solution. Whip on my handy dandy calculator to make sure I don't make any mistakes with my math. 0.02 times 0.085, and I get 0.0017. Now, acid is canceling base, so I subtract them. Do my little math, and I get 0.0019 moles of acid left. Okay, so that's what's remaining after I added it in my base, and I can see that because the base doesn't equal the acid. So that's the amount of acid, that's the number of moles of acid that I have left. That's not the molarity. Okay? I cannot stress that enough. This is the number one mistake that people make, is they say, oh, moles is molarity. No, it's not. It's the moles. So now I have to find the molarity of my H+. And to find the molarity of my H+, I take the moles remaining, 0.0019, and I divide by the total volume in the beaker. The total volume in the beaker is the 40 liters, I'm sorry, the 40 milliliters that was there of the acid before, plus the amount of base that I have added, which in this case is 20 milliliters. And of course, this is all converted to liters. So I have to, in this case, it's now 60 because I had 40 to start, I added 20 to it, so that's going to be equal to 60. When I do that math, again, this is 0.0019 divided by 0.06, and I get 0.0317 molar. Okay, now that's the concentration of H+, because that's the concentration of my acid. Remember, the molarity of the strong acid is equal to the molarity of the H+. Notice that quite a bit of it, a third of it, I'm sorry, I'm down to a third in concentration of my, I started with 0.09, and now I'm at 0.0317. Now I quick do my pH. pH is equal to the negative log of 0.0317. So I take negative log second answer, and I get 1.50 is my pH. Okay? So this is step 1, finding the moles of each of my substances. This is step 2, subtracting them to find out how much is left over. Step 3 is to find the new molarity, and then step 4 will be to find the pH. Now let's do it after 50 milliliters of sodium hydroxide has been added. So now this is a total of 50 milliliters. Now what I always do is I always start from scratch. Don't do something like, oh, well, this is the moles that are left after 20, and I've added 30 more, so now I'll find that, no, it gets too complicated. And you know what? You know my rule. I always go back to the given. So I never use numbers I used previously because you never know when you've made a mistake. So here I pretty sure I did it right. I have a decent amount of acid left over. My pH is acidic, so I'm pretty good. So I'm pretty confident in my answers, but I'm not 100% as confident in them as I am in the given. So when I go back, I start from scratch and assume that this is a new reaction where I'm just adding 50 milliliters. Now, remember from the previous slide that at 42.4 milliliters, I've hit my equivalence point. I am now beyond my equivalence point. So if I think about that titration curve, I'm up here somewhere. Okay? So I had better find, when I find the pH of this solution, my pH had better be greater than 7 when I'm done. So again, the process doesn't change. Find the moles of each substance that you had to start. Okay, so that was just from the previous problem and the previous slide. So now I have 50 milliliters of my 0.085 molar solution, which again, the math here is pretty easy, but I'm going to use the calculator just to be sure I don't make any mistakes. 0.05 times 0.085 is 0.00425. Okay, so again, step 1 is find the moles of each of your substances. Step 2 is find out how much has been neutralized and how much is left. So I subtract them. 0.00425 minus 0.0036 is 0.00085 moles. I'm sorry, 0.0065 moles. Now, this is moles of sodium hydroxide left. Okay? So that's how much base has left, because notice that my base is greater than my acid. Now again, this is a strong substance. So since it's a strong base, the concentration of my sodium hydroxide is exactly equal to my OH minus concentration. But I don't have molarity right now. I have moles. So I have to find the molarity of my OH minus. So I take the moles that are left, and I divide by the total volume in the beaker. I started with 40 milliliters of the acid. I added to it 50 milliliters of base, which is 0.09. Okay, so I take my moles and I divide by 90 milliliters, which is 0.09 liters, and I get 0.007222222 molar. So that's the concentration of my OH minus. Now, remember, if I now do the negative log of that number, that is not pH, because this is an OH minus. This is the POH. Okay? So if I take the POH of that number is 2.14. That is not my answer, because I know that I'm dealing with a base, and I know that my pH cannot be less than 7 for a base. So that is my POH. And remember that 14 minus the POH is equal to the pH. So my pH would therefore be 11.86, which makes sense because I have base as my primary substance. Remember, the first thing I said before I did the problem is on the titration curve, I'm above the equivalence point, so I had better have a pH greater than 7. I have a pH greater than 7, therefore my assumption is I did it correct. And that's how you do calculations of pH during titrations.